speaking of evolution, right? So computers and screens have gotten better, so this has become 8-bitified or whatever. So here's a really simple model that has lots of nice things in it. It's a fun thing to play around with. Random walks are great things, right? I like random walks, and I know I talked about them in POCs, but the world likes them too. You know, they appear in all sorts of ways. Randomness is a really big feature of everything. So here's a really simple little network model, right? So you can start to think, oh, you know, I want to erode a landscape, and I showed you this sort of elaborate one that Bruce Shaw and Marcelo Magnasco had made, and then lost. The only remains were a VHS cassette. It's pretty slim. So here's a ridiculously simple one, and you can think of sort of stuff falling down like paint on water on a glass or something, but it's more about sort of just a slope where there's some sort of erosion going on. And so it's a triangular lattice, because that's a great lattice, and at each point on the lattice you just flip a coin and say that the flow is going to go this way or this way. That's all, right? Very simple thing to do. So that's what this is indicating. And what's very nice about this is there's lots of random walk stuff in here. The first return problem is in here actually, which is a thing we highlighted in POCs. If you remember that, right, what's the probability that if you have flipping a coin, what's the probability if you start off at 0 that the number of heads minus the number of tails gets back to 0, right? So, you know, half the time you're back there in two flips, right? Flip a head, flip a tail, or flip a tail, flip a head. But actually, on average, we had that very odd result that you expect an infinite amount of time to pass before you get back to 0, which is really awful for gamblers. Well, they kind of deserve it. It's okay. Sorry, that was moralistic of me. Anyway, it's good for the people who make money out of them. So good. Wow, these are tough terms. So, but the probability that returns after L steps, and it has to be an even number, decays as L to the minus 3 halves, which is a really, really heavy tail, you know. Okay, so those things appear in here because what we have, and I'll show you this, is if you think about the drainage divide, right? So don't think about the streams. Like, well, let's start here and think about how big is this basin that starts here. Well, it's really the divides are actually random walks themselves. So you have 2 random walks going up here. And eventually those random walks will go, right? With probably one, we expect them to run into each other. But so you'll have these random walk boundaries, and so when they hit each other, that's the end of that little basin. So the typical length of a basin actually has exactly this probability distribution for the first return thing. It's that the probability that, pick an arbitrary point, the probability that it's a basin of length L, because here there's no fractal scaling, right? It's just the longitudinal length and the length of the basin of the actual stream will be the same up to some factor of whatever it is. And that will decay as L to the minus 3 halves. And so the area will be in there as well. So all right, so let's do these calculations, right? So the boundaries of random walks, as I just tried to explain, for the basins and their first return problems. This is then connects into all sorts of nice mathematical problems. It's actually, you can think of this as this is a hard thing to work with, but you can think of it as a partition of, and this is say, an area of a certain sort. We'd be interested in, you know, how many basins are there of a certain length, because then we sort of turned it this way, and also of a certain area, right? What's the joint probability distribution? So that's a difficult thing to work with, but it's interesting. And it's a kind of, partitions are very famous for, in pure math. This is something where it's an increasing partition. It's not just ordered in that way, right? We'd have to think about partitions of integers where it's ordered. They have to increase. So it's another kind of partition problem. Because we've got this random walk, right? It can't go back this way, right? We're thinking about time going this way. So that's just a little thing on the side. Might be fun for some people to think about. As I said, right, we've got these guys, and this is what pops out of all of that. Right, so this is actually the derived thing after n time steps, and n has to be even. This is the probability that your little random walker returns, right? It's sort of, yeah, it's going away, I suppose, but the framing was always that this is your drunk friend, right? Which is sort of like, it's not great. Just confused, right? They're confused. You let them go, and they take random steps away from where you are, and you're worried about them coming back. You should be very worried, because on average it will take them an infinite amount of time. So they should pack snacks. Okay, so L to the minus 3 halves. So we also expect, in a very sort of naive way, right, the typical excursion of a random walk, if we've got time here, it grows as t to the half, very famously, right? So the normal distribution for the location of that random walker, the standard deviation grows as t to the half. So we're going to expect that. We're going to have a length of n, and we're going to have a sort of a typical excursion of n to the half. So we're just going to multiply those things together. So the area is growing like length to the 3 halves, and length will be growing like area to the 2/3. So we have this very nice model where this is Hack's exponent, right? It's greater than a half, which is what you expect from dimensional analysis, right? Length is meters and area is meters squared, say. And so you find all of these things. You get this is the exponent for the area, probability of area. The area, you select a basin, it has an area of A, vector case is A to the minus tau. It's a 4/3, which is 2 minus 2/3, right? These all fit together, these scaling relations. Gamma is 1 over h, right? All these things are here. Tau is 2 minus h, gamma is 1 over h, they all fit together. There's no fractal scaling, so d equals 1. So this is a universality class where we could say these two things. We might want to say d equals 1 and h equals 2/3, right? That defines this network. So if we went out and found one in the real world and just measured some things, we'd probably look at it and think it looks pretty random anyway, but this is the sort of story where we'd say, oh, you know, it really is in this box. And one thing we've always been very interested in with systems is, are there these sort of discrete set of universality classes, right? There's this kind of network, and then maybe there are some other kinds, and there isn't sort of a continuum in between them, or maybe there is. And as I said, the Horton ratios are harder to define.